Section 5.5 is on theorems about roots of polynomial equations. Factoring a polynomial, p of x equals our basic formula for polynomial, and solving p of x is equal to 0 can be especially difficult if the leading coefficient, a sub n, and the constant term, a sub 0, have many factors. You can minimize the number of values you have to guess and check by using the rational root theorem. So this says that if you have this polynomial with integer coefficients, there's a limited number of possible roots of p of x equals 0. The integer roots must be factors of your constant term, a sub 0, and the rational roots, in other words, any possible fractional roots, must have a reduced form of p divided by q, where p is an integer factor of a sub 0 and q is an integer factor of a sub n. In other words, your possible rational roots are going to be the factors of your last term over the factors of your first term. And they show that here. So the first term is 21, and 21 actually has factors of plus or minus 1, 3, 7, and 21, and your last term is 10, factors of plus or minus 1, 2, 5, and 10. So all of the possible roots would be all of these numbers here. These would be your p's, right here, over all of your possible q's, which would be these numbers here. And as you can see, that would be a whole lot of numbers. And they actually kind of jump to the answer here. But let's take a look at an example and see how you might approach something like this. So this says, what are the rational roots of x to the third minus 5x squared minus 2x plus 10 equals 0? So this is my coefficient, my leading coefficient, okay, is 1, and my constant term is 10. So all of my possible p values would be all of the factors of 10. So that would be plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10. All of my possible q terms are going to be all of the factors of 1, which are just plus or minus 1. So then when I go to figure out what is p over q, I actually get just these values here because they're all being divided by 1. So plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10. So those are my possible rational roots. So that gives me 8 numbers that I should plug in there and see if they work. Here's an easy way to do it. Let's put this polynomial into our calculator, as I did here, and I'm not going to worry about graphing it. I'm just going to use the table to help me to evaluate that. So do second graph, and I'm going to put in those numbers. How about let's put in a positive 1, and what I'm looking for is when does y equal 0? Negative 1? Nope. Positive 2? Nope. Negative 2? Nope. Positive 5? That works. Let's keep going. Negative 5? No. Positive 10? Nope. And negative 10. So my only rational root, oops, negative 10 doesn't work. I know that one. There we go. So my only rational root is x equals 5. Now, I could have chosen, had all sorts of numbers. The main benefit to using the rational root theorem is it helps you to narrow down the number of possible values that you'd have to try. Okay. If you can find one root of your equation, then you can use synthetic division to factor the polynomial. So here's an example. What are the rational roots of x cubed minus 2x squared minus 5x plus 6 equals 0? So all of my possible rational roots, okay, are going to be the factors of 6 divided by the factors of 1. Factors of 1 are just 1 and negative 1. So my possible rational roots are going to be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. And I'm going to use the same method I did before and put this into my calculator. So here's my calculator, and I have that equation in here. So when I go to my table, and the possible values I was going to put in were plus or minus 1. Okay, I actually got 1 there. and I think I'll go ahead and use that. I also see I've already got -2 in there, but let's not go to that yet. Let's just use x equals 1. So from my calculator, I know that one of my roots is x equals 1. So I'm going to go ahead and do synthetic division using 1, pull off the coefficients, and doing synthetic division, bring down this 1. 1 times 1 is 1. Adding gives me -1. 1 times -1 gives me -1. Adding gives me a -6. 1 times -6 gives me a -6, which leaves me with a remainder of 0. So this is going to turn into x squared minus x minus 6 equals 0. And I can factor that into x minus 3, x plus 2. So my other two zeros in addition to x plus 1 are x equals 3 and x equals a -2. In lesson 4.8, we saw that the complex numbers a plus bi and a minus bi are conjugates of each other. In the same way, the irrational numbers a plus square root of b and a minus square root of b are also conjugates. The conjugate root theorem says that these roots must appear in pairs. So in other words, if one of my roots is a plus bi, there must be a minus bi also as a root. If one of my roots is a plus the square root of b, I must also have the root a minus the square root of b. So here's an example. A cubic polynomial, p of x, has rational coefficients. If 2 plus 3i and 2/3 are two roots of p of x equals 0, what is the other roots? So since it's a cubic polynomial, I know there will be 3 roots. So I'm going to have one root that is 2 plus 3i. Okay. I know that the other one is going to have to be 2 minus 3i, and then I have the root 2/3. Okay, so my answer is going to be x equals 2 minus 3i. Sorry about that kind of strange pause and explanation. I actually read the question wrong, and I did a whole lot of work in my notes that I didn't have to do. Let's move on to the next example. What is a quartic polynomial function? In other words, this is going to be something that has an x to the 4th in it, with rational coefficients, so that p of x equals 0 has roots of 1, 3, and 1 plus 2i. So I know that one of my roots is going to be 1, one of my roots is going to be 3, one of my roots is going to be 1 plus 2i, and I know by the complex conjugate theorem that I know the other root has to be 1 minus 2i. So I actually need to come up with the polynomial. So I'm going to have to do a whole lot of multiplying here. So if I subtract 1 from each side, x minus 1 is one of the factors. X minus 3 is another factor. Okay, this gets a little confusing. I have to subtract 1 and subtract 2i. So x minus 1 minus 2i equals 0. I know that kind of looks like a trinomial, doesn't it? And then x minus 1 plus 2i, I equals 0. Let me rewrite that, it's a little sloppy. 2i equals 0. Okay, so I have to multiply all of those out. Basically what I want is x minus 1 times x minus 3 times x minus 1 minus 2i times x minus 1 plus 2i. And that's what my function p of x is going to be equal to. Okay, let's break this down into two parts. Let's do this first. And that's just straightforward foiling. So that's going to give me x squared, and then minus x minus 3x is a -4x, and then plus 3. Now, multiplying these here is going to be a little more complicated because I've got like 3 terms in each of them. So I think I'll do that over here. So I'm going to take this x and distribute it to each term over here. So that's going to give me an x squared minus x plus 2i. 2ix. That was this x here times the second trinomial. Now let's do a negative 1. Negative 1 is going to give me another negative x. Negative 1 times negative 1 is going to give me a plus 1. Negative 1 times 2i is going to give me a negative 2i. Multiplied that. Now let's do a negative 2i times each one of those. That's going to give me a negative 2ix. That's going to give me a plus 2i. And that's going to give me a minus 4i squared. Okay, let's add up those terms. And you can see I kind of stacked some of them on top of each other because those will cancel out. Those will cancel out. This turns into a plus 4 because remember I squared is negative 1. And there's a plus 1. And there's a minus 2x. And there's an x squared. So cleaning that up, that's going to give me x squared minus 2x plus 5. So now I need to multiply that times what I had over here. To do that, let me give myself a little more room here. Whoops. I'm just going to put it underneath and do it kind of like a multiplication problem here. So I'm going to do this 5 times my trinomial on top. So 15 minus 20x plus 5x squared. Did that one. Now let's do 3 times each of those. Negative 6x. I'm sorry, negative 2x times each one of those. Plus 8x squared minus 2x cubed. Did that one. Now x squared plus 3x squared minus 4x cubed. I'm running out of room. And an x to the 4th. And then totaling all of those up, I will get that p of x is equal to x to the 4th minus 6x cubed plus 16x squared minus 26x plus 15. And that's my solution. That is a polynomial that has roots of 1, 3, 1 plus 2i, and 1 minus 2i. So in this section we took a look at theorems about roots of polynomial equations, the rational root theorem, which tells us how we can find some possible rational roots of our equation, the conjugate root theorem, which tells us that if we have a square root or an I in there, we have to have conjugates of each other, and then how to write a polynomial function if we are given the roots.